Cool. So yeah, that question actually a good segue. We're going to be talking more about sample sizes today and how to design experiments around sample sizes. But first, couple announcements. So we have homework 9 due Friday, 11:59 p.m. Pacific time, and actually all homeworks are going to be due on Fridays from now on. Um, Not necessarily they're going to be any harder or anything like that, but we just wanted to give you guys more time. So that's what we're going to be doing now. As you mentioned last time, all discussion sections this week are optional. Tomorrow's discussion sections are rescheduled, so check out the post on Piazza about that. We still will hold office hours tomorrow if you do want to come to office hours. Um, and tutoring sections are rescheduled as well. And then lastly, part of the reason why we're doing everything this week is so you can go vote. So please go vote. Cool. So on to what we're covering today. So today actually kind of just continues a discussion we've been having all of last week, all of last week's lectures. So we talked about center and spread on Monday, then we talked about the bell-shaped curve on Wednesday. Then on Friday, Professor Wagner went over a bunch of examples around variability in the sample size and how or variability in the sample average and how that relates to sample size. So we'll just kind of really quickly recap that today and then move on to how do you actually choose the size of a random sample. And then that's really important when you're kind of designing experiments. You're trying to decide to go out and collect data. Um, it can be helpful to understand beforehand how much data you need to collect in order to get a certain level of accuracy. And this is all going to be super relevant today because of the election and all the polling that's been happening recently. So hopefully today's lecture will help you get some more context around a lot of the polling data you've been seeing over the past several weeks. So firstly, to just kind of review averages of large samples. So we talked about how the central limit theorem basically says if your sample size is large, then the distribution of the average of your sample is roughly normal. And so again, that distinction is really clear. So your population data itself could look like anything. It doesn't have to look normal. But once you take the average of some data that's sampled from your population, that average itself is a random quantity. It's going to change every time that you take a sample of the same size. And so the way that moves around, the way that varies, that follows a normal distribution roughly. And that approximation, that normal distribution is more accurate of a statement the larger your sample size is. And so we saw some examples of that in the lecture on Friday. And what was also interesting was we saw that not only is your distribution of your sample average roughly normal, but it also gets thinner and thinner. So it gets tighter and tighter around the population average, the larger your sample size is. So if you're always doing a sample size of 100, you're going to have a bunch of different values that you could possibly get in your sample average. And it might vary quite a bit. But once you go to 400 or 900, the variability of your sample average starts to go down. So you can basically say that your estimate is most likely to be closer to the actual population average when you have a larger sample size. Intuitively, this makes sense. It's kind of like we have more data, we're going to be able to make a better guess. But it's actually a statistical fact as well. And so the way that sample average actually varies, that spread, we can actually quantify that. And so we can basically what we can say is we can approximate the variability under the assumption that it's normally distributed. So if we can assume that the sample average is roughly normally distributed, then we actually have a way to quantify what we can expect the spread to be, given that we know we're going to do a sample size of 100, let's say. And then the way we can do that is we say, well, this distribution of your sample average is going to be roughly normal, and the center is going to be the population average. So that's going to always be the case, regardless of what your sample size is. But the standard deviation, you can calculate it as the standard deviation in your population of all the values in the population divided by the square root of the sample size. And so basically what that means is as your sample size increases, this SD is going to decrease. So this SD over here, and this is SD is talking about the standard deviation of the sample average. So again, sample average, that's a statistic. It's a random quantity. It's going to change every single time that you draw a sample. And how does it vary? It varies based on what your sample size is. So larger sample size, the smaller it's going to vary. That's essentially what that's saying. And again, the power of CLT is that it doesn't matter how your data is actually distributed. You can have your data with a really weird left tail. It can have a right tail. It can be split up on two ends. You can have 3 bumps on it. It can look however it needs to look. but the average of your sample is still going to be normally distributed when you have a large enough sample size. That's the basic idea. And that's why it's so useful, because it, you know, in the real world, you don't know what your data looks like, typically your actual population data. That's why you're sampling. And so, you know, it might be hard to figure out what the distribution of your population is, but we can still get a pretty good handle on what like the average is. And typically the average is an interesting thing. Obviously, there might be cases where you care about things more than just the average. You might care about the maximum value or the entire range of the data. And so then it's a little bit harder to estimate those things. But the good thing is that the average itself, if that's the value you care about in your population, you can actually estimate that reliably and get a good sense of the variability of that estimate. So let's go back to our demo. So this is going to use a lot of this stuff from the last lecture. So we had our data set of the flights from 2015 taken from SFO and United Airlines. And so we had the delay of the flights here. So we've seen this data set many times. And basically we had a population mean of 16.65. That was kind of the average delay of the flights in minutes in the population. So this is, you know, we have all the data. So this wouldn't typically something that would happen in an actual study, but let's assume that, you know, we have all the data, and then the population standard deviation was 39.48 minutes. So pretty large standard deviation, meaning that the delay varies quite a bit. And then we created a function which would allow us to simulate one sample mean. And then that function takes in a sample size, and then it will draw a sample of that sample size and then calculate the average. So if you pass in like 100 here, it's going to simulate 100 random flights and then take the average of them. And then we create another function, 10,000 sample means. And so what this would do is it would do that process up above in this function, but do that 10,000 times. And so this is for the purposes of simulation. So, you know, you could then simulate doing like 100 samples 10,000 times and then see how much that sample average actually changes up every single time you do a sample of 100. And then finally, we created a function to like plot all of those sample means from your 10,000 random samples, or 10,000 simulations, I should say, and then just plot them all together on a graph. And so we did this once with a sample size of 100. So again, what plot sample means does is it says, we're going to take a sample size of 100, calculate the average value, and then repeat that process 10,000 times. And then that gives us this histogram. So these are all the different ways that we can get an average value of flight delay from 100 flights. And so you can see it's like centered around kind of our actual population mean of 16.65. And then the standard deviation of this sample mean is quite a bit less than the population. And it's actually about a factor of 10 less. And the reason for that is because of that formula. So the standard deviation of this distribution should be roughly equal to the standard deviation of the population divided by the square root of the sample size. So sample size is 100, square root of that is 10. So 39.48 divided by 10 should be roughly 3.948. And that's essentially what we get here. This is pretty close to 3.948. And so that's just showing you that relationship. And then similarly, if you do a bunch of simulations of size 400 in each simulation, then we get something that's even smaller. So now we're going to get something that's has a standard deviation of 1.94. So this is now tighter of a distribution. And so this is like roughly 2. And so this basically means that this is like about 20 times as small as the population. And so why is it 20? It's because we have this, a sample size of 400 in our sample. So when you're doing 400 in each simulation, then the square root of 400 is 20. So that means the standard deviation of your sample averages is going to be 1/20th of the standard deviation of the population. And then lastly, if you do 900, then it should be about 30 times as small because square root of 900 is 30. So this is just kind of showing you how that standard deviation of your average gets smaller and smaller, basically meaning that larger sample size, more confident we are of our estimate. There's less variability in the sample average. And so if you wanted to see this for like a bunch of different values of sample size, not just like 100, 400, 900, we've actually created this. And so if you are going to run this at home, like this is going to take quite a while to run. So you probably don't want to run it right now. But basically what this is going to do is it's going to create a bunch of different simulations. So they'll do a bunch of simulations of sample size 100, then a bunch of simulations of sample size 150, and so on. And then what it's going to do is it's going to show you what the standard deviation of the simulated sample means is. So this is the actual kind of standard deviation that we get in the particular in the particular simulation. And then it's also going to plot here what we would expect to get under the formula. So again, the formula is just kind of theoretical. This is what you should get if it's normally distributed. It's not going to be exactly normally distributed, right? That's what central limit theorem isn't saying, that it's exactly normally distributed, but it's like roughly. So this is kind of what we would expect. This is what we actually get. And so it's pretty cool to see how these are like super close. Like a sample size of 100, you would expect to see a standard deviation of 3.95. The reason we can calculate this is because we know the population SD. You typically won't know that in practice. Typically, you're just going to see this column. You're not going to actually be able to ever see this column. But in this case, we do have like perfect information. So it's useful to compare that here. And so here we can see you'd expect to see 3.94. We actually get 3.94, which is pretty cool. Once you start going up, you'd expect to see 3.22 if your sample size is 150. We happen to get 3.17 in our simulation, and so on. So you can kind of just see how it compares, but roughly these are pretty close, like almost to within 2 decimal places most of the time. So that's pretty cool. And then we even plotted them, all these values here, in a scatter plot. So on the x-axis here, we have sample size, and then on the y-axis, we have the standard deviation of your sample average. And so this is just showing that relationship here where as we keep increasing the sample size, the standard deviation, the variability of our sample average becomes less and less, gets closer to 0. And we're actually plotting 2 things here. So we're plotting the blue, which is the standard deviation of the simulated means. So that's like the standard deviation of our simulation. And then the gold is kind of what we would predict based on that formula. So the gold is just like the theoretical value from the formula. And so that's like if things were actually perfectly normally distributed, that's what you would get. And so you can just see how close they are. So most of the time, like the blue value, which is what we actually see in the simulations, pretty close to like what the formula would predict in the gold values here. So I went through that a little bit fast, but any questions about that? I want to make sure this is really clear before we continue the rest of the lecture. Oh, this is a good question. Does it asymptote to 1? So what that means, if you're not familiar with asymptote is, so basically, does this curve kind of keep going down all the way and then does it flatten out at 1? It actually flattens out to 0. So the formula is population SD divided by square root of sample size. So as your sample size becomes really, really large, if you take a number and divide by something that's like really, really large, it just gets closer and closer to 0 actually. So this standard deviation actually goes down to 0. So if you had like infinite data, essentially, you'd be able to estimate the population mean perfectly. So your sample average would be essentially like perfect. There would be no variability at all. You would just get the actual value. That's one way to interpret that. Closer to the bottom, the better. Yeah, that's correct. So the closer to the bottom, that means the more accurate your estimate probably is, the less variability there is in your estimate. So, in practice, you only get one estimate. You have one sample that you have, and then you're going to get the one estimate from that. And like, that's your best guess. But the idea is, how good is your guess? Like, how close is your guess? And so the larger your sample size, the closer your guess, the better your guess. Difference between blue and yellow dots. So blue dots are what we actually see. So let me go back up here. So like, let's say these are a bunch of simulations of sample size 900. So the blue dot would be the actual standard deviation we observe of this distribution here. That's the blue dot. And then the gold dot is like what would be predicted based on the formula. So in this case, what would be predicted would have been the population SD 39.48 divided by square root of 900. That would be the gold dot. So it's not really shown here, but it's kind of like a theoretical value that we would expect to see. Whereas the blue dot is like the actual observed standard deviation of your simulation. So your simulation itself is going to like vary a little bit. But that's basically what's being compared there. Is the population SD normally provided in the problem? It actually typically won't be. I mean, unless it's a problem where we say it is. In an actual like real life scenario, you're pretty much never going to know the population SD. The idea is you're just trying to get a sense of like what your variability is. And this is just showing through simulation that like the actual standard deviation, the actual variability, this is almost like a proof of why the formula is correct. So this is just showing you in practice, like the standard deviation of the actual simulations is going to be pretty close to the formula. So you can think of this almost as just like proving you that the formula actually works in real life. And how did we calculate both of these? So the yellow dots, again, it's just this formula, population SD, which we, in this case, happen to know, divided by square root of sample size. And then the blue dot is you just calculate the standard deviation of all of your simulations for that sample size. So these two dots here, for example, the blue dot is going to correspond to all the simulations you ran of sample size 200. What's the standard deviation of those values, of those averages? And then the gold dot is going to be the actual formula. So population SD divided by square root of 200. That's how we get the gold dot here. Cool. So this is basically what central limit theorem is saying. So if you know the population SD, you can figure out what the SD of your sample size should be. And so just kind of restating the central limit theorem here again as well. So the idea is this only holds if your sample is large and it's drawn at random with replacement. So again, it's really important to do with replacement. The main reason for that is because you want every single person that's being drawn to have the being drawn from the exact same distribution. So if you're taking, like, let's say your sample size is 1,000 people. If I draw that first person from a population of, like, I don't know, let's say 10 million people. Once I draw that first person, I need to put them back in because then I need the next person to be drawn from the exact same distribution. If I don't put them back in, if I sample without replacement, then that's going to mean that the second person has a slightly different distribution. They're sampling from like slightly less than 10 million people. Now in practice, like that doesn't really matter that much because it's like 10 million people. You take one person out of it. I mean, it's pretty unlikely you're going to sample that person again anyway. But that's kind of at least what you're supposed to do the correct way. And then again, regardless of the distribution of the population, the sample average, that has a variability that follows a normal distribution. Roughly normal, not exactly, but it's a good approximation. So with that in mind now, let's try to do this discussion question. So let's say we have a population and it has an average value of 70. The population has an SD of 10. So let's assume we actually know these things. Then one of the histogram below is the empirical distribution of the averages of 10,000 random samples of size 100. And they're drawn from the population. So which of these could correspond to this type of sampling from this population? So try to think through, it's kind of combining a lot of the stuff we've gone over today, but also just stuff that we learned about the normal distribution and how to like look at things graphically. Okay, so seeing a lot of A's and B's here. So let's try to figure out what this distribution should look like. So before we even look at the graphs here, actually, we should try to get a sense of what our distribution should look like. So we know we're taking 10,000 random samples of size 100. So basically we're taking a sample of size 100, and then we're doing that 10,000 times. So it's actually like 10,000 simulations. Each simulation has a random sample of size 100. And then it's taking the average of that 100 sample size. So we're basically gonna have 10,000 averages that we're plotting. So we're looking at the distribution of the sample average, and it's a sample average of sample size 100. So that means that the standard deviation of our distribution should probably be equal to the standard deviation of our population, which is 10, divided by the square root of the sample size. So sample size is 100, square root of 100 is 10. So that means 10 divided by 10 is what our standard deviation should be, roughly, of our distribution of our sample averages. So we should be looking for something that has a standard deviation of 1. Okay, so we know that. And then we also know that this distribution of our sample averages has to have an average that's like pretty close to the population average. So population average is 70. So this distribution should also be near 70, centered at 70. So if you look at these three distributions, they're all centered at 70. So they're all valid from that standpoint. They all have the right center. But now we have to look at the spread. And so we just said here that the spread should be 10 divided by square root of 100. So 10 divided by 10, and that's 1. So which of these, now that you know that it needs to have a standard deviation of 1, Now what would you say is the right graph? Cool. So now everybody's saying B. Perfect. Yep. And so the reason it's B is because we talked about how if something is normally distributed, the inflection point should be 1 standard deviation away from the center. And so, if you look here, the inflection point here roughly is like around 71, and 71, lo and behold, is 1 away from 70. So that's how we know. In C, it's 2 away. So this distribution here has a standard deviation of roughly 2. It's a little bit too wide. And then this one in A actually has a standard deviation of 10. So that's quite wide. That's basically actually the spread of the population. So this could maybe be what the population looks like potentially, but actually we can't say that for sure because the population need not even be normally distributed. It could be some other weird distribution. It might look completely different. So it kind of doesn't really correspond to it either. So B is the answer that we're looking for here. Oh, someone had a question here. So we're taking square root of 100 because that's the size of our sample within each simulation. 10,000 is how many times we're like doing the sampling. So 10,000 is the number of simulations. So the number of simulations doesn't affect the formula at all. It's really just the size of the sample within each simulation. That's what's important. If you did like 100,000 simulations, these graphs would look like basically the same. They wouldn't really change much. But what controls like how wide they're going to be or how narrow they are, that's the sample size within each simulation. That's what controls the spread of your distribution. And then, yeah, once again, to recap, if you know that your distribution is like normally distributed or roughly normally distributed, then the standard deviation should be kind of, the inflection point should be 1 standard deviation away from the mean. So we know that we're talking about sample averages here. So we can basically say, we know we're looking for a distribution that's roughly normally distributed. And we know that we're expecting to see a standard deviation of 1. So that means we should see a distribution that's centered at 70. And then the inflection point of the distribution is roughly around 69 and 71. And that's what we get here. So this roughly looks like the inflection point. And this roughly looks like another inflection point. So this kind of matches up with what we think we should be seeing. And again, these are the two things that we used here to kind of come up with what we expect the distribution to look like. So we expect the mean to be equal to population mean, 70. We expect the SD to be equal to population SD, which is 10, divided by square root of sample size. This is 100. So 10 divided by square root of 100 gives you 1. So you should see something with 70 and 1 as standard deviation. Cool. All right. So now to confidence intervals. So this whole idea of like approximating this with a normal distribution, like why is that even useful? It's because we can make confidence intervals a little bit more easily. So we've talked about how you can use bootstrapping to make confidence intervals of an estimate, like if you're trying to estimate like the median or any other parameter of your distribution of your population, you could use bootstrapping to do that. What's cool about sample averages, we don't even have to use bootstrapping. We can actually just straight up use the normal distribution because we know that our sample average is roughly normally distributed. So sample average is that one statistic where you can assume essentially that the distribution is roughly normal. And so you don't have to do any of the bootstrapping stuff here. And so again, we talked about how normal distributions are really special because there's like certain things that are interesting about like 1 SD away and 2 SDs away. So we talked about how if you're 1 SD away, on either side of the center, that's going to contain 68% of the data. So that's just a property of any normal distribution. And then similarly, if you're 2 SDs away, that's going to contain 95% of the data. So that means that if you know what the standard deviation of your distribution is, you should be able to create a 95% confidence interval pretty easily because you just need to find the center of your distribution and then 2 standard deviations away on either side. And you know that 95% of the data is going to be in there. And so how does this fact relate to, this is a fact about normal distributions in general. So how does this relate to sample averages? So we know that with sample averages, the distribution of your sample average, if your sample size is large, is roughly normally distributed. Its center is going to be typically like around the population average. It's going to have a standard deviation of this guy right here, population SD divided by square root of your sample size. So we just kind of know that. And so essentially what this is saying is, if we want to know, roughly where 95% of our sample average is going to lie, it's actually just going to be the sample average. It's going to be the population average plus our deviations. And someone just mentioned, is it supposed to be 1.96? Technically it's 1.96, but we pretty much just round that to 2 here. So that's why we're saying about 95%. And so essentially what this is saying is, if the population average is this gold bar, that means that if I take a sample of size n, whatever n is, then I can expect that 95% of the time, the sample average is going to be somewhere in this red region. So a sample average of a sample of size n, whatever n is going to be somewhere in this red area. So it should be within basically 2 standard deviations of that population mean. Similarly, though, what's interesting is this idea of distance, like how far away their sample average is from the mean. It's like symmetric. So what that means is, like, I can flip things around too, and I can say, if I know the sample average, that means I can say that, I can say the same thing about like the population average as well. And so the population average is probably going to be in that interval as well. So you can kind of like reverse the statements together. And so like, let's say we got a sample average like somewhere over here. We just happen to get that by chance. If I draw a similar set of 2 SDs on both sides of this point here, it is going to contain the gold bar. So you can kind of say the same statement if you know the sample average and you don't know the sample mean, which is what's typically going to be the case when you're actually like looking at data in the real world. And so that's why it's actually useful. One question is, what's the difference between the population standard deviation and the width of the interval? So the width of the interval is actually going to be 2 times, or actually 4 times. The width of this entire interval is going to be 4 times whatever is in here. And then what's in here, it's actually the population SD divided by the square root of your sample size. So again, this interval depends on your sample size. And again, now this is hopefully starting to make a little bit more sense, because the larger your sample size, the smaller the interval, the more confident you are in your estimate. So that's why they're all related together. And then one question was, how do we know that 2 SDs is 95% of the data? That's just a property about normal distributions. So 2 SDs on either side of the mean is going to contain roughly 95% of the data. This is just a fact about normal distributions. That's just how they're made. It's kind of interesting. And so again, if you wanted to actually construct this interval, what we could say is, for 95% of all samples, if you stand at the population average and you look 2 SDs on both sides, you'll most likely find your sample average. That's essentially what it's saying, at least in 95% of the samples. And then because that distance is symmetric, so the distance from the population average to whatever sample average you happen to get, that distance is the same regardless of which reference point you're talking about. Like if I'm at the population average, there's some sample average over there. If I go and walk over to the sample average, I'm just as far away from the population average as the sample average was for me when I was over there. So the distance is symmetric. And so basically what that means is, now if you go over to the sample average and then look 2 SDs on both sides of that, that's going to capture the population average 95% of the times you do this process. So it's kind of, you can make the same assumption there. So again, now basically what you could say is, if I know what my sample average is, if I can figure out a way to get the SD of my sample average, I can just go kind of like 2 standard deviations away on the other side, and like 95% of the times I do this process, the interval is going to contain the population average. And so if you wanted to calculate the total width of this interval, again, it's going to be 4 times the standard deviation. So if you go back here, why is that? Because we're looking 2 standard deviations to the right, 2 to the left. So if you add those up, you have 4. So basically 4 standard deviations, that's the width of your interval. And then what is a standard deviation? It's the population SD divided by the square root of the sample size. So again, this is assuming we know the population SD. So you can use this formula, if you know the population SD. Cool. So before continuing, actually, any questions about what we just covered? Oh, one question is, what would the width be for other confidence intervals? So for 95%, it's 2 SDs. For 68%, it's actually 1 SD. So that's just, again, not a property about normal distributions. So if you go back to, I think, last Wednesday's lecture, when we covered normal distributions, there was a table that we went over and you showed like within 1 standard deviation, it's 68% of the data. Within 2 standard deviations, it's 95%. Within 3 standard deviations, it's like 99.7%. So these are just facts about normal distributions. So that's kind of how we could change the width of the interval depending on like how confident we want to be. So 95% typically is like what people choose to do when they're reporting confidence. And then how did we get 4 SDs? Because we know that 95% of the data is within 2 SDs on either side of the average. And we just want to know what's the width of this interval then. So the width of the interval is just going to be 4 times it because we have 4 SDs here, essentially. So you have the sample average, 2 to the right, 2 to the left. So that means the length of this entire thing should be 4 SDs. 2 SDs on the right, 2 SDs on the left. What's the difference between the top and the bottom equation? They're equivalent. So the SD, we're just kind of plugging in the formula here, basically. So we know the SD of the sample average is equal to population SD divided by sample size, square root of sample size. So this thing should equal this, assuming the normal approximation, this central limit theorem. Cool. Okay, so now let's go to sample proportions. So proportions, we're mainly going to be talking about here is data that's just zeros or ones. So this is like a specific kind of data. So not all of your data is going to be like this, but a lot of interesting data in the world is just zeros or ones. And election data is a good example of this. So like, you know, is someone voting for Trump or not? It's like 0 if they aren't, 1 if they are. And then you might try to understand like what percentage of some county is going to vote for Trump. And so what you do is you go out, you do a sample of people, you ask whether they're going to vote for him or not. So you 0 or 1. And then you could just take the average, and that'd be like an estimate of how many people are going to vote for him in that county. And so we'll just go over something about data sets that are distributed with just zeros or ones. When your data can only take on values of 0 or 1, there's some even more interesting properties about that data that we can take advantage of. So firstly, what's cool about data that's 0 or 1 is that the proportion of things that are 1 is actually just equal to the average of the data. So let's actually show that to you. So let's say that we have these values in some population. So we have 0, 1, 0, 0, 1, 0, 1, 1, 0, 0. So we have 10 different values. 4 of them are ones. All right. And so the sum of this is 4 because there's 4 ones. So the sum actually just equals the number of ones. And then the average of this data set is 4 divided by 10. Because again, the average is sum of all the values divided by the number of values. So 4 divided by 10, that's 0.4. So that's our average. Average value of this data set is 0.4. Turns out 0.4 also equals the proportion of the data that's equal to 1. Because there's 4 ones and 6 zeros. So 40% of the data is ones. So that's one thing that's really cool about proportions. When you have like data that can only be 0, 1, the average value of your data set is the same thing as the proportion of your data that is equal to 1. And so just kind of extending this a little bit further, what this means is that the population average is the proportion of ones in the population, and the sample average is a proportion of ones in the sample. So basically, if you're trying to find like what proportion of a county is going to vote for a particular candidate, what we can do is just take a sample of people and then calculate the average value of their response. And the response can either be 0 or 1. So average value of that's an estimate of what proportion of people in the population are going to actually vote for that candidate. And so similarly going here, you know, with proportions, it's also really common that we might want to make confidence intervals. And one thing you're probably going to see a lot if you're looking at polls is like they report the margin of error. And they'll say like some states are within the margin of error or some counties are within the margin of error. And so that's related to creating a confidence interval essentially. And oftentimes you're going to see this number 3% come up a lot. So it's really, really common to see margin of error of 3% when you're talking about pulling data. And that just kind of see that number like really, really often. So it's kind of interesting. We'll go into kind of why that happens. But one way to think about, one thing that's kind of interesting about 0 and 1, right, is that this interval that you're going to make, it's going to be related to the population standard deviation, because the standard deviation of your sample average, that's going to be, you know, population ST divided by square root of the sample size, right? So that's going to be the same case here. And so the population ST, that's like the spread of your population data. And so when your data can be anything, you can have all different kinds of standard deviations in your population. But if your data can only be 0 and 1s, it's kind of interesting. Like your data is never going to be less than 0. It's never going to be more than 1. So it seems like there's some restrictions there on like what the spread can be. Like the spread can only be so much. You know, you're not going to get a spread of 100. That's not possible. You're not going to get a standard deviation of 100. Your data is only between 0 and 1. So there's some interesting things there that we can take advantage of. And so that's what we'll kind of talk about next. So again, if you wanted to know like the width of a confidence interval in the context of sample proportions, we would calculate it the same way. So your total width of, let's say, 95% confidence interval, again, it's going to be 4 times the ST of your population divided by square root of sample size. So this formula is exactly the same as what we went over in a few slides ago. But what's interesting here, right, is this ST of the population I just mentioned, it seems like it never gets that large because your data can only be 0 or 1. So if we can figure out like something about that ST, and we know like it's never more than like some certain value, that means that we can basically figure out this entire thing beforehand. So we can basically have some sense of what our accuracy is going to be before we even take a sample, which is kind of useful. Just if we know the sample size, basically, we could figure out roughly what our accuracy is going to be. And so let's say, you know, we wanted the total width of the interval to be no more than 1%. So let's say like that's what we want to have happen. How should you choose the sample size? That's kind of the question that we're going to try to answer. So we want this entire thing, we want our, the width of the interval to be 1%. That's the idea. So this is the width of the interval. And so this is how we would actually choose it. So what we would do is we'd say, we want everything here, this entire formula, to be equal to 0.01. That's 1%. That's how much we want the width to be. And so again, left side, 1%. That's kind of the width that we want our, you know, our study to have. And then the right side is the formula for the total width. And so if we just do some algebra here, basically if you take this square root of sample size, multiply it on both sides, and then take this 0.01 divided from both sides, this equation now transforms into something like this. So now we have sample size on the left here, and on the right we have 4 times standard deviation of the population divided by 0.01. And so as I mentioned, you don't typically know the standard deviation of your population beforehand, but we are noticing that like if your data is just 0 and 1, then it seems like the standard deviation can only be so big. So if we can figure out what that thing is, how big it can be, you know, what's the maximum it could be, then basically now we have everything on the right side solved for. We can plug in something into this, and now we actually have like an actual value that we can solve for. And then basically then we can figure out exactly what our sample size should be to get to a certain level of accuracy. In this case, 1% width of an interval, which would correspond to 0.25% standard deviation. So let's actually see a demo of this. So here we're going to simulate a 0-1 population. Oh, I think I didn't run my cell up here actually. So let me just run that. And so we have some code here. Let me just put this on another line so you can see it. So what this code does is it's going to simulate a population, or it's going to create a population of size 10. And then the number of ones here is just going to be specified. So we can choose the number of ones. So for example, if we do 2 as the number of ones, then it's going to create a population that has 2 ones and 8 zeros. And so how do we do that? So we're going to say 0-1 population, that's going to be a population, contains 2 arrays. So it's going to contain np.ones. So it's like, how many ones do you want? So we just want 2 ones in this case. We pass in number of ones, and then also zeros. How many zeros are there? It's 10 minus the number of ones. So this is just how we create a population. And so if you run this code here, we get 2 ones here and then followed by 8 zeros. So this is just a way to create that. And then if we run the standard deviation, if you want to see what the standard deviation of the population is, it has a standard deviation of 0.4. So now let's try it with some different values. So let's see what happens if we do like 4 ones. So now if we do 4 ones, our population has 4 ones followed by 6 zeros. And then if you want to look at the standard deviation of this guy, now we get a standard deviation of 0.489. So now the standard deviation has gone up a little bit. So it looks like we increased the number of ones, the standard deviation went up a little bit. So that's kind of interesting. And then if we do 5 ones, so let's say it's like 50-50, then we get a standard deviation of 0.5. So that's kind of cool. So if we have half of the data as ones, if half of our population is ones, we get a standard deviation of 0.5. And then now let's increase it further to like 7. So let's say we get like, there's 7 ones and 3 zeros in our population. So population looks like this, 7 ones, 3 zeros. Let's see the standard deviation of this. So now the standard deviation went back down. So it's kind of interesting. So now the standard deviation went back down to 0.48. And then if we go all the way, let's say we do like 9 ones. So now we have 9 ones and 1 zero. Standard deviation of that now it goes down to 0.3. So it's kind of interesting. So it seems like the closer the number of ones is to like half of the population, the higher the standard deviation is. But it doesn't seem to really go like more than 0.5. So we can actually make a graph of how the standard deviation of your population varies based on how many of the values are 1 versus 0. So that's what we've done here. So we created a function to do this. So first of all, this function just calculates the SD of a 0-1 population based on how many ones you have. So what it's going to do is it's basically going to just run these 2 lines of code together into one function. And then you can just specify the number of ones that you want to have. And then next, what we'll do is we'll create a table that's going to store the number of ones. So we're going to have like a bunch of different values of the number of ones that we want to try. We're going to try like 0 ones all the way up to 10 ones. And then we're going to just check like the portion of ones that are there. And then we're also going to have the standard deviation. So essentially what we end up getting is here we'll calculate the standard deviation of each of those different populations. And then we'll make a scatter plot with the results. And so in the end, this is essentially what we get. So here we're just plotting what proportion of ones you have in your population. And this is all of these have a population of just 10, and then what the standard deviation is. So if half of your data is equal to 1 and half is equal to 0 in your population, then you get an SD of 0.5. So that's kind of what we saw earlier. And then if you go all the way up to like 9, then you get an SD of 0.3. We saw that one earlier. And if you have 100% of your data is 1, standard deviation is actually 0, because all of your data is just at 1. There is no variability in your data. Everybody is just 1. And then if nobody's 1, everybody's 0, you also get a standard deviation of 0. Because again, if everybody's 0, there's no variability in the population. Everybody's the same value. And so you're just seeing this in a graph here, but it's kind of interesting. So you can see like basically the standard deviation like of your population data starts to go up, 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 but then it stops at like 0.5 and then it starts to come back down. And so this is with a population of 10. But this it turns out that this shape actually holds true even for a population of like 100 or 1,000 or 10,000, doesn't actually matter. They all have this kind of curving shape. So this is a very interesting property about 0-1 populations. So again, 0-1 populations are populations where the value only takes on either 0 or 1. So if you have data or some variable that's unique like that, so the variable only takes on either 0 or 1, the standard deviation is going to show this kind of curve, depending on what proportion of the data is equal to 1 or 0. So yeah, any questions? I'll stop for some questions about this before we continue. Yeah, so someone said, could this kind of data be tried true, false, red or blue? Exactly. So whenever you have any data where like, it's like 1 of 2 choices, you can convert it into like 0-1 data. So yeah, if it's like, is the state going to be like, democratically held or Republican held, like that's going to be 0, 1. So that's kind of different ways that you could have 0, 1 data essentially. But basically the main idea here is what this is showing you, this is essentially like a proof showing you that if you have a variable that can only take on either 0 or 1, the standard deviation of your population is never going to be more than 0.5. 0.5 is the maximum you'll ever see your standard deviation. It's not possible to have a standard deviation more than 0.5 when all of your data is either 0 or 1. Doesn't matter like how much of the data is 1 or 0, but you'll never get anything more than 0.5 as like the spread of your distribution. And so again, if you go back to this formula now, we know that this SD is never going to be more than 0.5. And so we can take advantage of that in this formula. So if you kind of put it all together, essentially what we can say is, we know this is the formula for our sample size. So we know that the square root of sample size equals 4 times the SD of our population divided by 0.01, assuming that we want an interval width of 1%. And we know that the SD of the population is never going to be more than 0.5. So if we take that into account, we can basically say that the square root of the sample size is always going to be greater than or equal to 4 times 0.5 divided by 0.01, because this value here is never more than 0.5. So this is never more than 0.5. That means the sample size, square root of sample size is always going to be greater than 4 times 0.5. Or not always going to be greater than, but basically, if we can guarantee that the sample size is greater than that, then we can make sure that we'll always have that 1% interval length. This is like how we can guarantee the 1% interval length, basically. So as long as our sample size satisfies this, we'll always have an interval width of 1% or less. So it's kind of a way to guarantee, regardless of what the population of the standard deviation or population of their standard deviation of your population is. And so if we know this, we can square both sides. And so then we get that basically, if the sample size is greater than 40,000, we'll guarantee a interval width of 1%. Doesn't matter what our population looks like. This will be true. And so this is really powerful and useful result. So basically we can kind of guarantee that like our margin of error is a specific value essentially. And so what does the 1% mean? The 1% just means the width of our interval. So again, our interval width is 4 times the standard deviation of the sample average. So in this case, the standard deviation of our sample average would be 0.025, or yeah, 0.0025, 2.5%. And so basically, if you want a 1% width of your interval, then you should have a sample size greater than 40,000. So this is just a way for us to guarantee that. And again, why can we make that guarantee? It's because we know that the SD of the population is never more than 0.5. And the reason why the SD of the population is never more than 0.5, that's shown here in the demo. So this demo notebook shows you like kind of different combinations of what proportion of your data is 1 or 0, because that's the only thing that can vary. When you have data that's 0 or 1, the only thing that can really vary is like how much data is 1 versus how much data is 0. And so you can just try like different combinations of that and then see like what the SD is. That's essentially what we're doing here. This is a simplified example. We only did it for a sample or a population of size 10, but you could do the same thing with a population of size like 1,000. You'll see the same curve. The SD, no matter how we like allocate the data in the population, the SD is never more than 0.5. That's essentially the idea. What does the 0.01 represent? So 0.01 represents the width of the interval that we want to get. So it's an arbitrary number that we chose. Like we said beforehand, I want this interval to be 0.01 wide. That's just what I want. And so if that's what I want, the sample size needs to be at least 40,000. If instead I wanted an interval of like 0.05, so I wanted an interval like much wider, like 5%, I was okay with having an interval that's like 5% wide, then the answer would be slightly different. So it just depends on what you want your interval to actually be. Is it always a percentage? In the case of proportions, it is. So when you're talking about proportions, when you're talking about data that can only be 0 or 1, your interval, typically you'll say that your interval is in the percentage form. Technically the interval is 0.01, but we can call that 1% because we know we're talking about percentages here. So it's just for this specific case. Is there something like this for a non-percentage? That's a really good question. So what if you're not talking about 0-1 data? What if you're just talking about like generic data, right? So if you have generic data, you're going to have this formula up here, but you're not going to know the ST of the population. So you can't really make the same claims unless you know something about the population. So there might be situations where we might ask you a question where we say, hey, we know the population of the ST is this. Given that, how big should the sample size be in order to get a certain interval? So you should be able to answer those kinds of questions using the same process we did here. The main key is you need to know some sense of like what this population ST is. Either we'll give it to you, or you can like assume something based on something about the data. Like in this case, if the data is 0-1, you know that this is never going to be more than 0.5. So you can plug in 0.5 here. Otherwise, you might be able to plug in something that we tell you. And then the thing that you divide by, that's also something that we'll typically tell you too, because we'll tell you beforehand that like, this is the interval we're going for. We want to make sure we have this kind of an interval. And so if you know those two pieces of information, then you can just follow the process on this slide to come up with what your sample size must be. And again, other thing to keep in mind too is the reason we're doing 4 here is because it's a 95% interval. So the question needs to be specifically about a 95% interval. If it's saying something about like a 68% interval, you're not going to use 4. You would use 2 in that case, because 68% is 1 standard deviation to the left, 1 standard deviation to the right. So that's a width of 2. So that's also important here. This 4 isn't something you would just use every time. Make sure you understand why we're using the 4. The 4 is because it's a 95% interval. Cool. I think we'll stop there a little bit over time, but I'll stay on for questions.